Hey guys, hope you're well. If you want to download this paper, just check the description below the video. Constructive interference takes place when... Okay, so before we even look at those, let's quickly talk about constructive, and then I'll also show you destructive interference. So let's say we have a pulse. Now a pulse is just a single disturbance, so something like that. And let's say the height of that is 3 centimeters, okay? And let's say we are moving in that direction. Now, let's say we have another one over here, which is, let's say that is 7 centimeters, okay? Let's quickly do this, do that. Okay, so this is 7 centimeters, and this one is going to the left. So when these two pulses arrive at each other, that is what we call interference. And we either get constructive interference or destructive interference. And this is all going to be based on the superposition principle. So let's just quickly make a note on that. Superposition principle. Okay? And this pretty much tells us that when two pulses meet, the overall pulse that is formed is going to be equal to the sum of the individual pulses, okay? That is not the word for word definition. That is just my explanation for you. When two pulses meet, you must add the individual pulses together. Okay, now we get two types of interference. When they meet, we get, okay, let's rather say when they meet, if they are, how do I say this? If they are both, actually let's do it like this. Sorry, I've got it now. When they meet, we either gonna get, when they meet, we will either get constructive, and that's when it looks like this. That's when you've got both of them being above, like that. Whoops. Or both of them are below, like that. Okay, that's gonna make it look like it's one drawing, doesn't it? Let's do it here. Okay, that's gonna be constructive or destructive. Let's do that in a different color. Destructive. Now destructive is when one of them is above and one of them is below. Okay, so superposition principle tells us that when the two pulses meet each other, you must just add the pulses together. Now you get two types of interferences. One of them is going to be constructive, where they're both on the same side. Can you see here they're both going down? Over there and over there. And then on this one, they're both going up over there and over there. That is called constructive interference. When one of them is above and one of them is below, then we get something called destructive interference. Okay, so let's carry on now. So then when these two over here combine, that is obviously going to be constructive interference. And what will happen is that, remember, according to superposition, we must just add these. So what is 3 plus 7? Well, that's just going to give us 10. So when they combine, it's going to go all the way up like that. So it's going to be a much larger one, which is going to be 10 centimeters, like that. And then, did you know that after they combine, then if they just keep going, then what will happen is that this one will just keep going to the left after this point over here, and this one will just keep going to the right, and it'll almost be like they've never even, it'll almost be like they never ever bumped into each other in the first place. So what it will look like is you'll have the 7 centimeter one over here and the 3 centimeter one over here. This one is the 7 centimeter and this one is the 3 centimeter. And the 7 centimeter will just be going on and the 3 centimeter will going on. So it's almost like they arrive at each other, they're then just going to combine, which is this part over here. And then after that, they're just going to carry on moving. So the 7 centimeter will just carry on coming out the other side, and the 3 centimeter will just carry on going out the other side like that. Okay, so let's see. Constructive interference takes place when the wavelengths of the combined pulses. Okay, now a lot of stuff here they're talking about is just like nonsense that we haven't really learnt about or even spoken about in grade 10. The wavelengths are smaller than the amplitudes. We never really look at wavelengths and then compare that with amplitudes. We do look at wavelength and we do look at amplitude, but we don't really look at them together. They're two sort of like different things. The amplitudes of the combined pulse is smaller than the individual. No. What we can realize is that the amplitude of the combined pulse is actually larger than the individual. Okay? So it can't be this one. And then the combined amplitude are in phase. No, we don't really talk about things like that. And then here, D, it says the amplitude of the combined pulse is greater than the individual. Yes, so that's the answer. A longitudinal wave is a wave where the particles in the medium, now they're going to talk about diagonal, adjacent, parallel, perpendicular. Let's quickly talk about the two different waves that we get. We get transverse waves, transverse, and we get longitudinal waves, longitudinal. Now, whenever I talk about a transverse wave, I always like to explain to students the idea of a Mexican wave. Have you ever been to or maybe you've seen it on TV, or maybe you have no idea, but I'm going to show you a little YouTube video now where I'll show you exactly what it is. But pretty much it's at like a sporting event. Let me actually show you. Okay, so obviously the video is on pause right now, but here we have something that's going to be a Mexican wave. So let me just play it so long, and then I'll talk about it. So look at all the people, okay? And look, can you see this wave coming over here? Here comes the wave with all the people. Here it comes, here it comes. Now watch what the people are going to do to keep the wave going. Okay, now watch how it keeps going. You see that? Let me just show you a little part again, in case you didn't see it. See this wave? It's like literally looks like a wave from the ocean. Okay. So what we saw was that we had this wave going around and around and around the stadium. Think about how amazing that is. The wave is going around the stadium, but what are the individual people doing? Are the people jumping to the left or jumping to the right to keep the wave moving left and right? No. The people, they actually just sit up or stand up and sit down, stand up and sit down. So the people, which we'll call the particles, they just move up and then they just sit down again. So they're just moving in this direction. But what was happening to the wave? Well, the wave was going around the stadium. And whenever you've got that happening where the particles are moving up and down in that direction, but the wave is going in that direction, then you see it makes a 90-degree angle. So that is called perpendicular. But that's not the answer, because that's a transverse wave. What we're talking about is a longitudinal wave. So longitudinal waves, they're different. In longitudinal waves, which is things like sound waves, you might have seen it in your textbook, but that's where you've got waves that look like this. So you've got like that, and then you've got areas that are more spread out, and then it becomes compressed again, and then you've got areas that are more spread out. And what happens is that if you had to see a simulation of this, I'll try to find one now, what you would notice is that the wave is going to move in this direction, and these individual parts, the particles, are also going to be moving backwards and forwards, but also in the same direction. Okay, I'm not going to go get a simulation now, just to save us a bit of time, but I do have videos on this already. So what happens in a longitudinal wave is that the particles, they move left and right, and the wave goes in the same direction. So can you see that these lines or these things, they are parallel, whereas here it is perpendicular. So in a longitudinal wave, the particles in the medium move parallel. The amplitude and frequency of a sound wave are both decreased. How do these changes affect the loudness and the pitch? Let's quickly talk about what amplitude looks like. So if you have a wave, that distance from here, let's put an arrow, that part there is called the amplitude. Now, when it comes to sound, the larger the amplitude, or the amplitude affects the loudness of a wave. So the higher the amplitude, the louder, and the lower the amplitude, the quieter. Okay, so it affects loudness. So if the amplitude of a sound wave is decreased, well, then the loudness is also going to decrease. So this cannot be the answer, and this cannot be the answer. Okay, so the answer is either going to be C or D. Now, when we look at frequency tells you how many or how often there are waves. So, for example, if you have something like this, that is going to be a much higher frequency than this, because in this specific area here we can see that there are more waves, and here there are less waves. So when there are more waves, we say that that is a high frequency, and when there are less waves, we say that that is a low frequency, because there are less. What does the word frequent mean? If someone goes to the shops frequently, it means they go a lot. If someone so high frequency means there's a lot of waves. There's a high frequency. So, and then you get the idea. So when it comes to sound, so when it comes to a sound wave, then this thing called pitch is like, it's almost like you could have like or you could have that is pitch. Okay, now the things I have to do for you guys. Now when it comes to sound, frequency goes with pitch. So a high frequency would mean a high pitch, and a low frequency would mean a low pitch. So they said that the frequency is also decreased, so that would lower the pitch. So there it is, and then we said this one is decreased, so the answer is C. The frequency of an electromagnetic wave has a certain wavelength, and they want to know what is the frequency. So when we are in the area of electromagnetic waves, we've studied these ones. We've got things like gamma, X-ray, visible light, infrared, UV, microwave. We've got a whole bunch of these different waves. They're not sound waves. They are their own specific kind of wave, which falls into a category of electromagnetic. Now, there is another one, radio. There's 7 of them that we typically look at. So these are those waves. Now, when we are busy in this section of electromagnetic waves, we've got this formula that goes E equals to HF. Okay? Now, E is the energy. H is Planck's constant, which is just a constant number that they'll typically give you on the formula sheet. And then F is the frequency. And then the other formula we have is C equals to the wavelength multiplied by frequency. Your teacher might use a different, instead of a C, some teachers use V, but they're both the same thing. So this over here is the speed, this here is frequency, and then this here is wave length. So which formula do you think is going to help us? Is it going to be this one, or is it going to be these ones over here? Well, let's see. They say they're asking for the frequency. They gave us the wavelength, and so we are going to use, we're definitely not going to use that one. So we're going to use this one over here. Now remember, the speed, it's amazing. When we are dealing with these waves, their speed is always a constant. That is a value of 3 times 10 to the 8. And so you can literally go plug that in, 3 times 10 to the 8. And then the wavelength is 2.1 times 10 to the minus 6. And then we just have to find f. So to get f by itself, you're going to divide this side by 2.1 times 10 to the minus 6. And what you do to the one side, you do to the other side. So that these can now cancel. And so if you had to go calculate that, if you round off to 2 decimal places, you should get 1.43 times 10 to the 14. Oh, but we can just choose from here. 1.43 times 10 to the 14, there it is there. John wants to decrease the resistance of an electrical circuit and has the following options. He can either increase the length of a conductor, he can increase the thickness, or he can use a copper instead of nichrome. Which combination of his options would best reduce the resistance of the circuit? Okay, so this is very easy, but for those of you that maybe find this a bit tricky, let me just explain. So let's talk about this thing called resistance. I know it's something that we talk about in electrical circuits, but let me actually just make this very easy for you. So we know that we have a piece of wire, okay, because we can see here increase the length, increase the thickness. So we've got a piece of wire. So there's the wire, and we must understand that inside a wire, you've got electrons. And those electrons are trying to move, okay? Now, if you make it very difficult for them to move, then that means you have a high resistance. Resistance, what does the word resist? It means to try stop something. So if there's a high resistance, then it means it's very difficult for the electrons to move. And if there's a low resistance, then it's very easy for them to move. Okay, so if you increase the length, so let me try show you this. Let's say we have a circuit, okay? And you've got a circuit that does this. Okay, so there's your circuit, right? Then in another circuit, you just have that. In which one do you think it's going to be easier for the electrons to be able to get around? Like they're going to get around faster. Well, it's definitely going to be this one, right? It's just a quick pathway, whereas here the electrons have to go there and there and there and there and there. So it might not necessarily be more difficult for them to flow, but it's just going to take the whole process a little bit longer. And so what I just want you to take away from this is that larger length or like a longer length, oh no, that doesn't sound right, a longer circuit generally means higher resistance. Okay, and then obviously the opposite is true. If you have a short circuit, then it's typically a lower resistance, like if you have a piece of wire. Okay, so if John wants to decrease the resistance, he should not increase the length, because when you increase the length, you're going to increase the resistance. Okay, now what about increase the thickness? Now what do we mean by thickness? Because that could be misinterpreted. What they mean by thickness is the following. If you're looking at the wire from the back, okay, they're not talking about this part over here as the thickness. They're not looking at that like that. No, what they actually mean is this, or this part of like this circle that I've drawn versus that. That is what they mean when they say thickness. It is the actual thickness of the part where the electrons are flowing. So the electrons are actually going to be flowing through this area and through this area. So into the page and out of the page, through that little area there and through that area there. So what you should understand is that the more space you give these electrons, so now they have all of this space to be able to flow, the easier it will be for those electrons to flow. So the higher the thickness, the lower the resistance. Lower the resistance. Okay, and then if you make it very narrow like this, if it's very narrow, then there's less area over here for the electrons to flow in and out of the page, and so you make the resistance higher. So if John wants to decrease the resistance, should he increase the thickness? Yes, because when you increase the thickness like this, then you have more area over here, and it's just easier for the electrons to be able to flow. It's like if you're watering your garden with a hose pipe, would you rather have a very narrow hose pipe, like a very, very narrow one, or would you rather have a thick one? Well, if you've watered a garden before, you would know that a thick one will actually allow you to output more water, whereas a narrow one doesn't allow you to output that much water. It's the same idea, okay? And then this one I found is a bit unfair to ask you guys. Should we use copper or nichrome? It's not like we all have a little booklet that we can just quickly look up, is copper less resistant than nichrome? But then what you must remember, if you look at all the electrical cables that we use in real life, in your house, obviously like if you're in your bedroom right now, there are cables around you. Now, obviously the cables, they've got like a plastic around them, because otherwise you would get electrocuted every time you touched it. But if you had to cut open the plastic wire, or cut open the plastic, and you actually look at the wire itself, I don't know if you've done it, you would see it's like a brown, red kind of, reddish kind of color. And that is copper. In life, everywhere in the world, we use copper as our conductors. So that should make you realize, why would we use copper and not nichrome? That must be because copper obviously has a lower resistance. We want low resistance. We don't want to make it difficult for the electrons to flow, because that's going to make electricity more expensive. We want it easy for electricity to be able to flow. That is the cheaper the cheaper option. And so the fact that we use copper in real life and we don't use nichrome, that should be a hint that copper is obviously better. So copper must have the lower resistance. So if John wants to lower the resistance, should he use copper instead of nichrome? Yes, he should. And so number 3 is also correct. So the answer is going to be D, because we want to use number 2, where we increase the thickness of the wire, and then number 3, we use copper instead of nichrome. The maximum work done per unit charge. Okay, so don't worry about maximum. If you just look at work done, that's W. We've spoken about that before. When we look at electricity, we've spoken about formulas that have I, Q, and T. We've spoken with formulas that have V, I, and R. We've spoken about formulas that have V, W, and Q. So here they're saying work done per means divide, unit of charge. Now charge is Q. So they're definitely looking at this part over here, and we should remember that we have this formula that goes, we've got the triangle that goes W at the top and then V and Q at the bottom, and we've learned how to use these triangles before. But the idea is that the maximum, yeah, I guess that is important, but in fact that'll actually be very important. But this is still quite a challenging question. So it's definitely got something to do with voltage. Now voltage is EMF, but it's also potential difference. So it's going to be either this one or this one. I will explain shortly. So it's definitely not going to be this one. It's definitely not going to be that one. Okay, so now when you walk into a shop, okay, the next time you walk into a shop, I want you to go look at the battery section. And what you're going to find, for example, is a AA battery, okay? A AA battery. Now that AA battery is going to typically say, it's going to have a specific kind of voltage. Sometimes it's going to be, or the most common you'd see is a 1.5 volt. That 1.5 volt is the best case scenario. That is the maximum voltage that you could get. But obviously, because in real life there are inefficiencies, maybe something, there are imperfections within the battery, and so in real life maybe you're going to get like 1.4, for example. But this maximum that you could potentially get, we call that the EMF. So because they use the word maximum over here, it is actually going to be A. So I do apologize that earlier I said we need to ignore that. I hadn't actually looked at these options, but the maximum that you can get out of a battery is the EMF. A positively charged rod is brought near the following objects. They said, yeah, which of these objects will not be attracted? Okay, so let's quickly go draw this out. So we have a charged rod. So it's just a rod like this, and it's positively charged. Okay. Now, if you had to bring that close to a small uncharged piece of paper, or pieces of paper. Okay, so here we've got a whole bunch of little pieces of paper. Now, just because they said the paper is uncharged, it doesn't mean that there is, it doesn't mean that, well, how do I explain this? Okay, let me try to explain this a bit better. So here's a piece of paper, okay? Now, in the paper, there are still going to be positives and negatives. It just means that the overall charge balances out so that it overall is uncharged. But the point is that there are still positives and negatives. Almost everything in life has positives and negatives, unless they've charged it negatively or positively, okay? So if you had to bring this rod close to this piece of paper, for example, well, what will happen is that, or let's say you put the rod, let's say you bring the rod to that side over there, then what would naturally happen is that all of the positive charges will move away, because remember, opposites attract and like charges repel. So what would end up happening is that these positives would end up going on one side, and then the negatives, because they are attracted to the positive, they would end up going onto this side, and then you would actually notice that there would be an attraction between the positively charged rod and the pieces of paper. So there would be an attraction over here, okay? So they said, which of the following objects is not going to be attracted? So number one, we don't want to have number one as part of our answer, because the uncharged piece of paper would be attracted. So the answer cannot be A, it cannot be B, because they both have one in it. Okay, let's move on. So the next one, a thin stream of water. Okay, so if you have, this is quite interesting. So if you have water, let's say we have water flowing down here. Now what we must understand is that water consists of H2O. So water is H2O. So if you had to go look at the shape of water, it's got something like that. And you're going to learn more about this in grade 11, but the hydrogens are positively charged and the oxygens are negatively charged. And so once again, we've got negatives and positives, and so the negative part will be attracted to this area and the positive parts, they won't. And so what would happen is that the water molecules, as they're busy falling, they would arrange themselves like this, where the oxygens will be facing the positive rod, because the oxygens, remember, are negative, and then the hydrogens will be more further away because they are positive. And so you're going to have a whole bunch of these water molecules falling, and the negative oxygens are going to be attracted to this. And so what you would actually notice is that, let me just draw this a little bit further away. What you would actually notice is that the water stream is actually going to start doing, it's going to start bending towards like that. These negatives are going to be attracted to the positive, and it's going to start bending the water stream. So the point I'm trying to make is that this positive rod will be able to cause a thin stream of water to bend towards it. So which of these objects will not be attracted? Well, a thin stream of water will be attracted. So this also cannot be part of our answer because it has 2 in it. So the only answer then has to be D, and let's see what D actually is. Or let's see, yeah, it says 3. So 3 is a positively charged balloon. That makes sense. If this is positive, and then you look at a positive balloon, so let's say we have a positive balloon over here, we know that like charges repel. And so if both of these are only positive, well then of course they're not going to attract each other, they are going to repel. And so the answer for this one must be D. A rubber balloon obtains a negative charge when rubbed against a rabbit's fur. Okay, which of the statements best explains why this happens? So let's say, for example, we have a balloon. Okay, there we have a little balloon, and we've got some rabbit fur. So I'm just going to draw it like that. So this is the balloon. Oh, I knew that was missing. There we go. And then let's just say this is the fur. Now let's say they are originally neutral. So they don't have a specific positive or negative. They just have a balance, and so they are neutral. And let's say the same is true with the rabbit fur. Okay, just got a whole bunch of positives and negatives floating around. Then when you bring them into contact with each other, okay, and you start rubbing them together, electrons are going to flow. So the first thing I need you to understand is that it is only the negative electrons that are able to move. We don't have the ability to move the positive things. It's only the negative ones that move from one to the other. So maybe it's going to go from the balloon to the fur, or maybe it's going to go from the fur to the balloon. So that's the first thing you must understand. Only the negative charges are transferred. So the answer cannot be B, because that says positive charges, and the answer cannot be D, which says positive charges are transferred. We can only transfer negative charge. Okay, now we've got to try to figure out if the negative charges go from the balloon to the fur, or if it goes from the fur to the balloon. How do we do that? They tell us that the rubber balloon became negative. Okay, so would that not mean that there were a whole bunch of negatives that went over to the balloon? So because they went over to the balloon ended up becoming more negative. So the negative charges are transferred from the rabbit fur to the rubber balloon. So the answer must be A. A small metal sphere A has a charge of -4. Okay, -4 nanocoulombs is placed on a stand. Were electrons added or removed? Okay, so that's a bit of a weird question to ask, but what they mean is the following. They mean, imagine that you originally have a sphere A and it doesn't have a charge. That means the positives and negatives are perfectly balanced, and so the overall charge is 0. Then they tell us that the charge is now -4. So, because remember, all things in life would have a charge of 0 unless we do something to it to give it a specific charge. So how would you go from here? How would you change it to that? How would you make it more negative? Would you add electrons to it, or would you remove electrons? Now remember that electrons are negative. Electrons are negative. So if you took this thing over here, how would you make it more negative? Would you take electrons away, or would you add more electrons? Well, you would add more electrons, because if you add electrons, then this whole object ends up becoming more negative. So it says here, were electrons added or removed? For 1 mark, we're just going to say electrons were added. Then it says, how does the number of protons, which are the positive things, compare with the number of electrons, which are negative, in sphere A? Write down less than, greater than, and give a reason for your answer. Okay, that's a very easy question, guys. When you have equal numbers of protons and electrons, then what would your overall charge be? Well, that would equal 0, because your positives and your negatives are the same, so it would balance out. But when you have a charge of -4, then that means it's got more electrons, right? So it would have to have more electrons than protons. Because if electrons are more than protons, then object will be negative. And if your electrons are less than your protons, then the object must be positive. Okay, so how does the number of protons compare to the number of electrons? Well, the number of protons will be less than. because they said, how does the protons compare? So we'll say the protons are less than, and then we can just say that, sphere A is negatively charged, which means it has more electrons than protons. Or you could even say less protons than electrons. Whatever you want to do, just remember it's got more electrons and less protons. This question says that 10 to the power of 13 electrons are now added to sphere A. Calculate the new charge on sphere A. Okay, now I don't want you to just jump and think about formulas. I want you to actually think about this carefully. So we've got the sphere A, right? Here's sphere A, and it's currently -4. So because it's negative, it means that it already has a lot of electrons, because electrons are negative. Now we're going to take 10 to the 13 electrons. Do you know how many that is? That is so many electrons. The number 10 to the 13 is 1 with 13 zeros. 6, 7, 8, 9, 10, 11, 12. They are going to take that many. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. They are going to take that many electrons, and they're going to go add them to this molecule. So that this charge or sphere. This sphere is then going to become what? Even more negative, because every single electron is negative. And now they're going to go add that many electrons to it. Okay? Now, on our formula sheets, they tell us that if you take one electron, it has a charge of negative, because we know electrons are negative, 1.6 times 10 to the negative 19. This is the charge of one electron. Okay? Now imagine you have this many of those. What would the overall charge be? Well, wouldn't you just multiply those two numbers together? Now remember, we do have a formula for that, where this number over here is number of electrons. This over here is the overall charge. And then this here is the charge of an electron. So we know that this is how many electrons we have. It's 10 to the 13. So we could fill that in over there. So let's just go clear up a bit of space here. So we could say 10 to the 13. Now, we don't know how much charge that is going to be. Remember, I told you we should just multiply them, but this formula is going to do it for us. Now, when we use this formula, we don't put the negative of the electron, so you just keep it as a positive. Okay. Now, if you had to go get Q by itself, you would realize that you're going to end up multiplying these two things, but that's also what we said over here. It makes sense. And so we're going to say 10 to the 13 multiplied by 1.6 times 10 to the negative 19. And that gives us, it's either going to say 0.00345516 coulombs, or you should write it as 1.6 times 10 to the negative 6 coulombs. Okay, so that is how much charge this is over here. Now, they want to, and remember, it is actually negative. So we don't put a negative on the formula, but we must remember that that is negative because they are electrons. So imagine you've got a situation where you've got the sphere, right? And it's already got a charge of -4 nanocoulombs. What is nanocoulombs? We need to talk about that. Remember, we've got these 4 different things. You've got millicoulomb, microcoulomb, nanocoulomb, and picocoulomb. Now, to convert them, we use times 10 to the minus 3, times 10 to the minus 6, times 10 to the minus 9, and then times 10 to the minus 12. So if we have this one, then we could actually rewrite it as -4 times 10 to the negative 9 coulombs. Okay. So imagine you have this charge, which is -4 times 10 to the negative 9, and then you add even more negative things to it. What would the overall charge be? Well, you could say -4 times 10 to the negative 9, and then you add that new charge on, and so you're going to end up minusing, and so you're going to end up with a final charge for that one of, let's write it up here. Alright, you should end up with negative 1,604 times 10 to the negative 6 coulombs. If you did, if you did want to, you could also write this as, you see how times 10 to the minus 6 is microcoulomb, so you could also write it as minus 1,604 microcoulomb. So both of those are correct. Two identical spheres B and C are placed on stands, and they each have a charge of they have a charge of 4 times 10 to the minus 6 and negative 6. So which one is which? Well, it says B first, and then that means this will be the first one. Okay, so that would be B. So B would be, that's when they use the word respectively. So it's going to be 4 times 10 to the minus 6 for this one, and then negative 6 times 10 to the minus 6 coulombs for this one. Okay, now they said that the spheres are allowed to touch each other, and then after touching they are separated and brought back to their original positions. First question, state the principle of conservation of charge. So what the conservation of charge tells us is that in this system over here, for example, there is a specific amount of charge, okay? So let's say we have a big box around the system, and we have a certain amount of charge, like we said. Now, you can't create any more charge or any less charge than what we already have. All that will happen is that electrons are either going to move from that one to that one, or from that one to that one. But the overall charge in this system cannot change. There are no electrons coming in from the outside, and there are no electrons escaping to the outside. So the overall charge stays the same. So if we look at the principle of conservation of charge, it says charge cannot be created or destroyed. So we're not adding in more charges from the outside, and we're not removing charges, for example. Okay, it can only be transferred from one object to another. So like we said, it could either go from C to B or B to C, but the overall charge will remain constant. Okay, so you could say that for that question. Now, explain what occurs as the spheres touch, and then explain why this reaction occurred after touching each other. Okay, very, very easy. Let me try to help you understand this. So all it is the following. We must understand that inside these objects, any objects in life, we've got protons and electrons, okay? But let's just keep it to these two. We've got protons and electrons, and this one has more electrons. Why do you say that, Kevin? Well, see how it's negative? Now, we know that electrons are negative and protons are positive. So if this charge is negatively charged, or it's more negative than this one, then this one must have more electrons. So this one has more electrons, okay? And when you make objects touch, what happens is that the electrons are going to try to balance. So it's going to try to happen that this one that has a lot of electrons, or has more electrons, it's going to start giving some of its electrons over to B. It's going to start doing that for a little bit. And eventually, what will happen is that the overall charge of this object will actually end up becoming more negative, and this one will end up becoming more positive, and eventually their overall charges will be exactly the same. It's like this. Let's say this one is -4 and this one is 2. Then if this one gives 1 electron over, then this one will become +1 because it will become more negative, and this one will become a little bit more positive. Then this one gives another electron over to B, so then this one will become a little bit more negative, so it will go down to 0. This one will become a little bit more positive, it will go up to 2, or -2, sorry. Then it gives another electron over, so this one will now become even more negative, so it will become -1. This one will become more positive, and it will then go to -1. At that stage over there, there is no more electrons being transferred because now there's a balance. And all of a sudden, these two things, they look at each other and they're like, hey, I don't want to stand next to you anymore. And the reason is that like charges repel. But just before they were like charges, it looked like this. And so here they were not like charges, and that's why they were still attracted to each other. But as soon as they did that last little transfer, suddenly they become like charges, and then they repel from each other. So that is all that happens when you put two objects next to each other. The one that has more electrons, or the one that has the more negative charge, will just start giving its electrons to the other one. It's like, hey buddy, I want to be your friend. Would you like a sandwich? And then it keeps giving sandwiches, keeps giving sandwiches, keeps giving sandwiches. And suddenly they realize, we now look the same. And they're like, dude, I gave you too many sandwiches. Get away from me. You're toxic. You're stealing my sandwiches. So it's a weird relationship. Okay, so I hope you never forget this. So that is what happens, okay? So explain what occurs as the spheres touch each other. Okay, so when the spheres touch, electrons are, remember, it's only electrons that can move. You don't move protons, it's only electrons. When the spheres touch, electrons are transferred from C, and then I'm going to put in brackets here the more negative charge, the more negative sphere, to B, which is the more positive sphere. Okay, so it says explain what occurs as the spheres touch. That's what happens. Explain why this reaction occurs. And then you can say until the what do we can say? Until the electrons are evenly distributed at this point, the charges are equal and the spheres will repel each other. Okay, so they want us to calculate the number of electrons, but we don't know how much charge is transferred. So we're looking for this, we know this, and there is a way to find this. So let me show you. We know that this B was originally that, and this C was originally that. When they then come into contact, we said electrons are going to go there, and then they're going to move apart. Now there is a formula that allows us to calculate what, remember we said that eventually this one and this one are going to have exactly the same charge. Remember I used the example of -1, and then they're just going to move apart. There is actually a formula that allows us to easily calculate if you take these two, and then you can work out what it ends up becoming for each of them. And that is the formula that you've definitely seen before. It goes Q equals to Q1 plus Q2 divided by 2. Okay, so what it means, and sometimes teachers put the word nu here. So what it means is that you take the original charges, which is this one. Okay, I'm not going to have space there. So 4 times 10 to the -6 plus -6 times 10 to the -6 divided by 2. It's almost like you're just taking out the average. Like if you take the number 6 and you add it to the number 10, or sorry, what is the average of 6 and 10? If you got 6 out of, let's do this. If you got 60% for one of your exams and then you got 80% for another exam, what is your average? Well, your average would be 70. So you would say 60 plus 80 and then you divide by 2. It's exactly what we're doing here. We're just saying that if you take this one and you take this one and then you add them and divide by 2, you're just finding the average, and that's how it works. And so what you would end up getting here is you're going to end up with -1 times 10 to the -6. Now, that doesn't mean that that's what you're going to use over here. No, not at all. You got to think about this carefully. And we should say Coulomb over here. If this one goes from 4 to -1, how much did it change by? How do you go from 4 to -1? Wouldn't that be a change of 5? Okay, from 4 to -1. And what about this one? If this one goes from -6 to -1, how much is that change by? or to go from -6 to -1, it's also a change of 5. But that's correct. However much this one goes, however much this one's charge changes, this one would have to change as well. So if this one changes by 5, this one would also have to change by 5. Okay? Because as this one loses an electron, this one gains electrons. Right. So now we know that the amount of charge the amount of, oh no, we haven't actually written that part. So we could say that the Q, or the charge that is transferred, is just going to be, now you could either use B or you could use C. I'm going to use B. So I'm going to take the new charge, which is -1 times 10 to the -6, minus the old charge, which is 4 times 10 to the -6, and that's going to give us -5 times 10 to the -6. Okay, now, where are we? Okay, so now we can go and use this formula. But now when we use this formula, we always keep this as a positive, and we always keep this as a positive. Okay, so the number of electrons is then going to be the amount of charge that was transferred, which we've now calculated. We're going to keep it as a positive, as 5 times 10 to the -6. And then the charge of an electron, although it's negative, we keep it as a positive in this formula. And if we work this out, we end up with 3.125 times 10 to the power of 13. And there's no units for that. It's just number of electrons. So we can just say it like that. And that's it. Grade 10 learners want to investigate the relationship between current and potential difference. Their teacher gives them the following apparatus: a voltmeter, ammeter, connecting wires, and 5 cells. The table below shows the results. Write down a possible investigative question. Okay, so let me just quickly first talk to you about it. So what they have is they've got some wires, and then they've got some cells. So let's say, for example, we know that this is a cell, right? So let's connect 2 cells quickly. So there's 2 cells, and let's go and have a wire. So there we've used the cells, we've used the wires. Now if we want to measure the current, we use something called an ammeter, and then if we want to measure the voltage, we measure it like that with a voltmeter. So what these learners did is they decided to try out different amounts of cells. So maybe they use 2 cells, and then they measure the voltage, and they measure the current. Then what they do is they maybe take away, add a 3rd cell, and then they do the same process all over again. They go measure the ammeter, and they go measure the voltage. And then they went and repeated this. You can see 5 cells. They've done it 5 times. So one of them is 1 cell, 2 cell, 3 cell, 4 cell, 5 cell, for example. And then they go measure the current. So what could an investigative question be? Well, for example, you can see that these numbers are pretty really structured, right? So these are the ones that the learner were changing. They were changing these ones. They were adding 1 cell, then they added 2 cells. Then the ammeter reading, you can see that these numbers are pretty random. So they changed this, and then they measured what effect it would have on that. So we could say, for example, how does voltage, or let's call it potential difference, how does potential difference affect, and then we've got here current. Because we know that this one with voltmeter, that's potential difference, and then this one here is current. So how does changing potential difference, or how does potential difference affect current? This one says name the dependent. So now you got to be careful. Independent is the variable changed by the person who's doing the experiment. So I'll say, for example, changed by the student. The dependent, this is the one that is, it's the outcome. So they change the independent variable, and then that causes something else to change, and that's the dependent one. So how could we define that? It is the variable that gets, or let's say it's the variable that we measure after changing the independent variable. There we go. That makes sense. Okay, so what is the dependent variable? Well, we know that the learners are changing the voltmeter, so that is your independent. That is your independent, because independent is the variable changed by the student. And then what is the dependent variable, or what is the thing that we were measuring? That is your ammeter reading. So this would be your dependent variable. So we can just say here current. Don't say ammeter. Ammeter is just what you use to measure, but it's actually the current. What is the control variable? The control variable is the thing that you don't change. So it's the variable that is not changed. And so very often you won't even see the control variable mentioned. So it's a bit of a tricky question, but what we must understand is that we usually measure voltage with current and resistance. You know how we have like the V equals to IR, VIR formulas. So if we're measuring voltage and current, then the other one that they don't really talk about, that one usually has to remain constant. Because we know that all three of these affect each other. So it would not be right for us to change the voltage and then measure the current, but then we're also changing the resistance, because then we don't know what is causing the change. Is it the voltage that's changing, or is it the resistor? And so you only want to test two variables at a time, and then you keep the other one constant. So the control variable will be resistance. This question says, draw a graph of the potential difference versus current. So that's going to be very easy, because we literally have the values. I don't know why they said the word difference. That's a mistake. It just meant current. Plot the points and then correct them with a best fit line. Okay, let's do that. So if we now draw a graph, on the x-axis, you always put your independent. Remember, that's the one that the person can change, but let's not call it voltmeter, because that's just the device you use. Let's call it potential difference, and that's measured in volts. And then on the y-axis, you always put your dependent, which is the one that we measure after we've made the change. So that would be your, no, don't call it ammeter, that would be your current. Okay, now it's easy. We're just going to go plot values. So it goes up in 1.5. So I'm just going to do like even spaces over here. And so 1.5, 3, 4.5, 6, 7.5. Now with these ones, I see that it's going to go from 0 up to 3 point, let's say up to 3.5. So we're going to go 0.5, 1, 1.5, 2, 2.5, 3, 3.5. Okay, so 1, let's just put 1, 1.5, 2, 2.5, 3, 3.5. Okay, now let's go plot our first point. So 1.5 and 0.7, that would be about there. Then 3 and 1.4, so 3 and 1.4 would be somewhere there. And then 4.5 with 2, so that would be there. And then 6 and 2.7 there. And then 7.5 and 3.4 there. And then they said, draw a graph and then plot the points and then connect them with a best fit line. So a best fit line, obviously it'll be better for you because you have a ruler. It doesn't have to go through the origin. So you're literally just going to do something like on your ruler, you might realize, or you might see that these points are not going to be perfectly on a straight line. So you might get something like that, where this dot is not necessarily on the line. In grade 12, you'll learn a lot more about best fit lines. As long as you're getting pretty close to all of the dots, that's good enough. So it says plot the points and then connect them with a best fit straight line. Now, this one says, from the graph drawn, deduce a relationship that exists between current and potential difference. So look at this. We can see that as you increase the potential difference, so as the potential difference increases, then the current increases. So as you increase the one, you increase the other. Ooh, and then I just realized while I was looking at this graph, how would we get 7 marks? Well, you get 7 marks for that, and then you also have to put a heading. So we could say current, which is your y-axis, versus voltage, or potential difference, sorry. Okay, and that'll get you your 3rd mark, and then they gave you a mark for your line, and then marks for your points, and so yeah. But I did forget about that. That's important that we look at that. And then from the graph, deduce a relationship. Okay, so when we say that if you increase this one, then this one also increases, that is called a direct relationship. So we can say that current is directly proportional to potential difference. There we go. The circuit below shows 2 light bulbs, 4 ohm and 5 ohm. Okay, so here we've got 2 light bulbs over here connected in parallel. Okay, so let me just explain what we have here. Here we've got a 4.5 volt battery, so these are just cells. Now, here we have the light bulbs, and then these devices here, those are just ammeters. They are just measuring, and here's another ammeter. Those things are just measuring the current. They're not doing anything besides measuring. Okay, and then here we have our cells. Now the first question says, calculate the effective resistance of the circuit. So here's where you would go find all of the resistances, and you would put all of the parallel ones together, and then you would add that all up together with the series ones. But we don't have any resistors in series, so we only have these two which are in parallel. Now remember, when you are in parallel, you add it together like this. R1 plus 1 over R2, and so 1 over R parallel is going to be 1 over 4 plus 1 over 5, and so 1 over R parallel, you can just go put this on the calculator, and so that's going to give us 0.45, and that's going to give you 9 over 20, and then all that you do is you just flip both sides upside down, and so that's 20 over 9, which is 2.22. So 2.22 ohms. This one says, calculate the total current in the circuit. So we know that we have the VIR triangle, and we know that current is I. So if you want to get I alone, it's V over R. And so the voltage, this is an easy question because we know that we've got this voltage, and we know this is the total circuit voltage, and this over here is the total circuit current, and this here is the total resistance. So we could literally just go and say 4.5 divided by 2.22, and that'll give us 2.03 amps if you round to 2 decimal places, 2.03 amps. This question here says, calculate the amount of charge passing through in 10 seconds. So we also know that we've got other formulas, which is the Q, I, T formulas. Now they said calculate the amount of charge, which is Q, and they've given us the time. So if you had to get Q by itself, remember, that becomes I multiplied by T. Now we know what the current flowing in the circuit is. It is 2.03 amps. And then the time must always be in seconds, which it is. And if we work this out, you're going to get 20.3 coulomb. Okay, this question 5.3 says, calculate the amount of charge passing through the ammeter A2 in 10 seconds. Okay, so we need to know the ammeter, we need to know the charge going through there. So we know that charge, we can find it from the Q, I, T triangle. Now, charge is, if you know how to use this triangle, you're going to have to multiply these two. So I multiply by T. So they've given us the time, but we don't know the current flowing through here. Okay, now remember this little formula that I've showed you guys before if you've watched any of the grade 10 lessons on electric circuits. We know that the voltage of the battery, which is 4.5, is equal to the sum of all of the voltages that are in series, but you see there are no other voltages in series, so that part will just be, you ignore that, plus all of the voltages in parallel. So this will be, but we don't know what the voltages in parallel are, so we're just going to put, well, let me fill this in a bit better. For this part here, sum of voltages in series, we're going to put 0 because there's nothing there. And then we don't know what the voltages in parallel will be, so we'll just put here parallel branches. And what we can then see if you solve this equation is that the parallel branches are then going to be equal to 4.5 volts. And so why do I have a little asterisk over there? Well, it means that the reason I say that is that all of the parallel branches will be the same voltage. So we've just worked out that the parallel branches are going to be 4.5. So that's going to be 4.5 volts each. So this is going to be a 4.5 volt branch, and this is going to be a 4.5 volt branch. Okay? Another way to think about it is the following. Imagine you are a little electron, okay? And you start your journey over here and you make your way through the circuit. Here you go. And by the way, when you came out of the battery said, "Hey electron, I see you going on an adventure. I'm going to give you 4.5 volts so you can go and enjoy your adventure. I'm going to give you some, you can think of it as like an energy. I'm going to give you some, let's just say I'm going to give you some voltage, okay? Now that little electron is going dee 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 dee. Now when that when that little electron gets over here, it has to make the decision as to whether it's going to go up or down. It cannot do both. So let's say it decides to go this way. So now it's going to go like this, like this, like this, like this, like this. And when it gets back to the battery's going to say, "Hey, I hope you had a good adventure and I hope that you used all of your voltage." Because if you used all of your voltage, it means you had a lot of fun and you were using all of your voltage to do fun activities. The battery does not want the electron to arrive back here with any leftover voltage. The electron has to use all of the voltage in the circuit. So the only place where that electron had to use it would have been when it went through the light bulb. So that means the voltage of the light bulb must be 4.5. Now let's take another electron's journey. Let's say we have another electron called Todd. Now here comes Todd. Todd also came out of the battery, so Todd was also given 4.5 volts, and Todd comes along. Now Todd's a little bit different, so he's like, he's more of like he's like this huge guy. He just gyms a lot. So now when he gets here, he also has to make the decision to go up or go down. So this time, Todd, well, this person, Todd, he goes down. And so he goes through this way, and then he gets back. Now, when he gets back, the battery still says to him, "Hey, Todd, I really hope that you've used up all of the voltage that I gave you, because that's the way electric circuits work." And so Todd, he would have had to have used 4.5 volts over here. And so we can see then that it makes perfect sense that the voltage going across both of these must each be 4.5, okay? So it's going to be 4.5 for this light bulb and then 4.5 for that light bulb. All right, so now why did we need that? Oh yes, so the reason we needed that is we're trying to eventually calculate the charge going through A2, but we know that charge is equal to current multiplied by time, and we don't have the current. We don't know what the current is over here. So now we can use I equals to V over R, but we're only using it in this part. And so that's going to be equal to the voltage now, which is 4.5, over the resistance of that one, which is 4. And if we simplify or divide, that'll give us 1.125. Don't round off because it's not the final answer. And now we can go use the QIT formula. And then the time must always be in seconds, which it is. And that's going to give us 11.25 coulomb. This last one says that another resistor is now connected in series next to ammeter A1. So maybe we can just go put it over there. So there we've got a resistor. How will this change affect the total current of the circuit? Right, what we need to understand is that, let's say you are a little electron and you are busy flowing over here. Boom, 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 boom. Oh no, now you got to go through a resistor. These electrons, they don't really like flowing through resistors. Think about the word resist. Resist means to stop, to try stop something from happening. So if there is a resistor, like a light bulb or a microwave, all of these devices, they have a resistance. And those resistors make it more difficult for the electrons to flow. So by adding another resistor over here, it's going to make it more difficult for those electrons to flow, and so it's going to cause the overall current, which is how fast the electrons flow, it's going to cause the overall current to decrease. Okay, in answering 5.4, we're going to say, they said how will the affect the total current? We will say that the total current will decrease, or they said decreases. And then the reason for that is that the overall circuit resistance increases, which will cause the total current of circuit to decrease. It makes sense, hey guys. If you try to resist something, you're going to try to slow it down. Like when people are playing rugby and someone's running towards you with the rugby ball, you're going to try to tackle them because you are the resistor. You are trying to resist the flow. Two or more pulses can pass through the same medium at the same time in the same place. When they do, they interact to form a different disturbance. The resulting is obtained by using the superposition principle. Okay, so let's just quickly talk about this, guys. So we know that, for example, because they're making it sound very complicated here. We know that if you have a pulse, right, like that. Whoa, come on, Kev. And then let's say we've got another one. And let's say this one is going this way and this one is going this way. We've looked at this before, right? If you've watched the lessons on waves, and when these two pulses arrive at each other, all that's going to happen is, so when they arrive over here, you're just going to have this smaller one, which is this one, and then this bigger one is going to add onto that one. So it's just going to add to that one, so it's going to go like up to there, and so the total height will just be the sum of both of them added together. Okay, we've learnt about that. That's pretty straightforward. And then we also know that if one of them is above and the other one is below, then when they meet each other somewhere over here, well, then you're gonna minus their amplitude, and you're gonna end up with a wave, or a pulse, sorry, that's a little bit smaller, maybe like that over there. Let's do it in a different color, or let's do it dotted. It would be something like that, maybe. Okay, because it would be this one minus that one. We've looked at that. Okay, now when they both are on the same side, so you see how this one's above and this one is above, and they meet each other and they make each other, and then when they combine it becomes bigger, that is called constructive interference. Okay, and then when they meet each other where they are on opposite sides, then we call that destructive interference. Okay, and both of those fall under this thing called the superposition principle. So for the principle of superposition, now your teacher, there's slightly different definitions that go around, but you can obviously use whatever your teacher uses. But pretty much we can say something like, when two, okay, that's not how you write two, Kev. When two disturbances, each of these are disturbances. When two disturbances occupy the same place at the same time, okay, like when we said that these two are going to occupy the same place at the same time, the resulting disturbance is the sum of the individual disturbances. So for example, if this one is 3 centimeters, if this height over here is 3 centimeters, and this height over here is 4 centimeters, then when they combine, that'll be 7 centimeters. However, if, for example, this one over here is 2, and this one over here is 8, then your overall would actually end up being 6, because you would say 8 minus 2, because they're on opposite sides. So when they are on opposite sides like that, you subtract them. Okay, moving on here now. So destructive interference, which was this one over here that we spoke about, takes place when two pulses meet and result in a smaller amplitude disturbance. Yeah, that's correct. Here we have a 8 and a 2, and when they combine, we only have a 6. So you see how we go from a big 8 to a smaller 6, okay? The amplitude of the resulting pulse is the sum of the amplitudes of the two initial pulses, but the one amplitude will be a negative number. Yes. Use the theory of destructive interference to draw two pulses of different amplitudes meeting from different directions to demonstrate this theory. Okay, so that's very easy. What they want you to do, for example, is you could show that, and then let's make it a bit of a bigger one like that. And this one, for example, is going that way, and that one is going that way. And then the result of that, well, what would be the result? The result would look something like this. Let's make it a bit smaller. Or let's make it a bit bigger than that, though. So what we're trying to show here is that this one and this one, when they combine, the result is gonna, you see this one is a little bit, this one here is a little bit bigger, and then so the result is still gonna go down like that, but it's gonna be a little bit smaller than this one, because you're gonna end up minusing them. So for example, if this one is 2 centimeters and this one is 8 centimeters like we showed earlier, then this would be 6 centimeters. Okay, but they don't need you to put any numbers on right now, so you don't have to put that. All that you need to show is this and that. This one says that a pulse covers a certain distance of 37.5 centimeters in 1.25 seconds. Calculate the speed. So when we talk about pulses, then we don't use this formula, because that's only when it comes to waves. But a pulse is just a single one. That is a pulse. A wave is when you have this. Okay? So when it comes to pulse and you want to work out speed or distance, then we use the distance, speed, time formulas. Okay? So they want us to calculate the speed. So we know that speed is then equal to distance over time. Now you see how they want the answer in meters per second, but here we have centimeters. So remember that if you want to convert distances, these are the common distances we need to be able to convert. Let's make this a bit bigger, sorry. Kilometers, meters, centimeters, millimeters, and then there's always 1,000 here, 100 here, and 10 here. When you go this way, you multiply. When you go this way, you divide. So we are going from centimeters to meters. So because we're going to the left, we must divide, and we're going to divide by the number in between them. So we're going to divide by 100. So we're going to say that the distance is going to be 37.5 divided with 100, and that's 0.375. And so that gives us 0.375 over the time of 1.25, and that'll give us an answer of 0.3 meters per second. A transverse wave is traveling along a string. A point on the medium carrying the wave is observed. A graph of displacement versus time is shown. The vertical distance between the crest and trough is 3.2 centimeters. First question, define a transverse wave. So a transverse wave is like, you know, at a rugby stadium where sometimes people in the crowd, you'll be sitting there, or you've seen it on TV, and then suddenly there'll be like this wave going around and around the stadium as people are sitting and standing and sitting, and then you see this wave going around. That is a transverse wave, because the wave is going around the stadium, so it's going from like maybe left to right, but the actual people, those people that are making the wave happen, they are sitting and standing, sitting and standing. So the people are standing, and then they're sitting. So the people are moving in this direction, but the wave is going around the stadium. And so you see there's a 90-degree over there, and that is what a transverse wave is. It's when the particles, which are the people, move at 90 degrees or perpendicularly to the wave, which is this part over here. So a transverse wave is a wave in which the particles move perpendicular. That means 90 degrees. That looks like this. Perpendicular to the direction of motion of the wave. This one says, how many full waves are there between 0 and 0.21? Okay, so remember, let's go. That is one wave, okay? So you mustn't say that is one wave. A wave has to have the up part and the down part. So that is one. Then let's do another one. So here comes the next one. 2. And then let's do another one. Well, let's do that a bit better. 3. So there are 3 waves. Okay, now from the information given, write down the amplitude. Amplitude is so you got to take the middle position, which is over here. Okay, and then you got to look at this distance over there. That's the amplitude. But now they haven't given us everything. But then they did say that a graph of displacement is shown below. The vertical distance, okay, but now be careful. The vertical distance between a crest, the crest is the top one, and a trough, that's the bottom. They're saying that that distance is 3.2. 3.2. But that is not the amplitude. The amplitude is only to the center. So you're going to divide that by 2. So you're going to say 3.2 divide by 2, and that's going to be 1.6 centimeters. This length would only be 1.6 centimeters. This question says, calculate the period. Okay, so we've got some formulas for period. One of them is to remember that period, which is a T, is 1 over the frequency. Another one to realize is for period is that, or maybe that's good enough. Let's just see. 1 over frequency. Okay, another one is to also remember what is period. What is it? It is the time for one wave, whereas, or let's rather say seconds, whereas frequency is the waves in 1 second. So you see they're almost the same, but they're totally different. They look the same, but like this is so similar. So period says how many seconds do we need for one wave, whereas frequency says how many waves will there be in 1 second. So if we look carefully, we can see that there are 3 waves in 0.21 seconds. So how many seconds do you need for one wave? Or you could then say 0.21 divided by 3, and that'll be 0.07 seconds. This one says, if the wavelength is 0.4, remember wavelength is this distance over here. It is literally the distance of one wave. So then this would also be 0.4 because that's also a wave. And then this would also be 0.4 because it's one wave. Okay, so if the wavelength is that, calculate the speed. Now we know that there's this formula that we use, V equals to F times wavelength. So we want to calculate the speed. That's the unknown. We know the wavelength. They gave that to us as 0.4. We don't know the frequency, but we do know that there are these 2 formulas. T equals to 1 over F and F equals to 1 over T. So frequency is 1 over period. And we already worked out the period as 0.07. So we could then work out the frequency as 1 divided by 0.07. Now don't round off because this is not the final answer. And so let's just get rid of all of this. So it's going to be 14.2857. Yeah, that's good enough for now. And so we can then go and fill that in over here. So we can say V equals to frequency. We can actually just leave the frequency as 0.07. I just realized it's not going to be difficult to write it as a fraction like that instead of having to carry this. And then the wavelength is 0.4. Then you can go type that all on your calculator, and then we can round to 2 decimal places. So 5.71, and that's going to be in meters per second. 5.71 meters per second. Grade 10 learners study the relationship between frequency and wavelength for different types of EM. EM stands for electromagnetic, and there are 7 types that we look at in grade 10. Remember, they are things like microwaves, radio waves, infrared, visible, X-ray, gamma, and then UV. And remember, the formulas that we use in this chapter would be E equals to HF. These are the things we use when we're talking about electromagnetic waves. And we also use this formula over here. Instead of using the V equals to F that we normally use with normal waves, when it's electromagnetic waves, we change the V to a C, because this is always going to be 3 times 10 to the 8, because electromagnetic waves always have the same speed, and that is 3 times 10 to the 8. Okay, so these are the common formulas we're going to use here. Now it says define the term electromagnetic radiation. Now in grade 10, there are different definitions from different teachers. So you can just use whatever your teacher uses, but one of the things we could say is that the electromagnetic radiation is a self-propagating wave having electric and magnetic components. Arrange the following types of EM radiation in order of increasing wavelength. Okay, so remember, we have with these kinds of electromagnetic radiation, we said that there are 7 different types, and if we arrange them, I'm just going to arrange them quickly. So we know that the one with the most frequency is gamma, then it's X-ray, and then we have what were they again? Let's just write them down. Micro, radio, UV, visible, infrared, X-ray, gamma. Is that 7? 3? Yeah. Okay, so gamma is the most highest frequency, then it's X-ray, then it's UV, which we get from the sun, then it's visible, then it's infrared, and then we have micro, and then radio. But now let me quickly speak to you guys about this. So have you ever heard that X-rays, if you do them, have you ever been for an X-ray and the person who gives you the X-ray, do they stay in the room with you, or do they usually go out the room? They go out the room. Why? Because X-rays are very energetic, and if you expose yourself to that too often, it can cause things like cancer. So X-rays look like this. High energy, okay? So as you go from radio, so radio is nice and chilled, and then it gets, so radio is, it does this. Let me try to show you. It goes relaxed, then it starts getting more energetic, and then it's very energetic, okay? So can you see that the wavelength is very long in the beginning? The wavelength is very long. So as we go this way, the wavelength increases. You can see with these shorter ones, look how short the wavelength is. It's so short for a wave. So when you have a short wavelength, then you've got a high frequency. So as you go more to the right, then your frequency increases. So this one here, the radio wave, has a low frequency, high wavelength. This one has a high frequency, low wavelength. Okay, so it says, arrange the following types of EM radiation in increasing wavelength. Okay, so as we go this way, the wavelength increases. So which of these have the smallest wavelength? Well, that would be gamma. So we'll put here gamma first. Then it's going to be X-ray. Then it's going to be ultraviolet, which is UV. Okay, so we've done this one, done this one. Then it's going to be visible light. And then it's going to be infrared. Now this one says, UV radiation is dangerous and it can cause skin cancer. Explain how this radiation causes cancer when your skin is overexposed. It's like a biology exam. Okay, so what we can say is that UV light has high frequency, which can penetrate the skin. Okay, and that's also like why X-rays are so bad if you do it over and over. So especially someone who works at the X-ray department, if they, they're probably doing like 20 X-rays a day. If they stayed in the room, it wouldn't be really healthy for them. But because you only have an X-ray maybe once every 5 years, that's very low exposure. But for someone who works there every day, if they had to stand there every day and get penetrated by these X-rays, it is very dangerous. Okay, now it says here, give one use for each of the following types of EM radiation. Now, guys, when I was a student, I hated studying these kind of things. I just wanted to do calculations. I literally hated all of this. Ugh. I still do, to be honest. I actually just want to do these questions. Just give me that calculator, boy. So, give one use for each of the following types of EM radiation. Okay, so X-rays. Well, you've been for an X-ray before. Well, most of you probably have. Sometimes it's to check whether you've broken a bone. So to scan, to check whether you broke a bone. Microwave. I wonder where we use that. Oh, yes, the microwave that we use in our house. So we could say heat up food. Heat up food. Calculations. Here we go. Calculate the wavelength of a radio wave that has a frequency of that. Okay, very easy. Well, not like super easy, but we can only use these two formulas in this chapter. So they want us to calculate the wavelength. So this is the unknown, and they give us the frequency. So what we could do is, oh, and of course we have that. Oh, easy. So we have that. Remember that that's a constant. I even wrote it over there. And then they gave us that. And so, yeah, we don't need that formula at all. So we can just say 3 times 10 to the 8 equals to the frequency, which is 2.1 times 10 to the 8, and then wavelength. Now, to get wavelength alone, you would have to divide by 2.1 times 10 to the 8 and divide by 2.1 times 10 to the 8. Because what you do to the one side, you do to the other side. And if you had to go do this, you should end up with, if you round off, you should get 1.43 meters. The particle nature of light, which can be demonstrated by the interaction of photons with matter. One way in which light interacts with matter is via the photoelectric effect. Okay, so this is actually something you're really going to go into detail with in grade 12. Grade 10, it's just something quite small. Some schools don't even consider asking you this definition, but it says define a photon. So I'll just explain it very basically. We know that there's light all around us. Now, some people say that light travels as a wave, and then other scientists say that light travels instead of a wave, but they say it rather travels like this with these little particles. And then some say, oh, well, maybe it just does both. Maybe it just does both. And we call this the dual nature of light. It has a wave, but it also has individual little parts. Now, these individual little parts are called photons. Photons. So it says the particle nature. See, so as I said earlier, some scientists believe that light travels as a wave. Others say that it travels as particles. So we call it the particle nature of light. Now, each of these is called a photon. And to calculate the energy of that photon, we typically use this formula over here from electromagnetic radiation. And then remember that when we have that formula, we also very often use this one. And this is all from electromagnetic waves. So what is a photon? A photon is a small little packet of light, and it has energy. So the definition that you could use, and there's different definitions at different schools, different teachers, but it is a packet, which just means like a little piece of energy of which light is composed. So they're saying that light is oh, let me just write this, composed. They're saying that light is built up of these little packets of energy. So each little part has energy. Okay, now the infrared beam emitted by a projector remote has a wavelength of that. Okay, so they've given us wavelength. Calculate the energy. So they eventually want us to calculate this. So can you see how this will work? We're going to use this formula first, because remember, infrared, microwaves, UV, gamma, X-ray, UV, visible light, the 7 that we look at in grade 10, they all have the same speed, 3 times 10 to the 8. So we could use this formula. So we could say 3 times 10 to the 8 equals to frequency multiplied. Ah, sneaky, sneaky. We've got to be careful. So that catches a lot of learners. So remember, just like we see with electrostatics, we need to remember that you need to know how to convert. So this one is always times 10 to the minus 3, times 10 to the minus 6, times 10 to the minus 9, times 10 to the minus 12. So to convert this to meters, you would say 1.3 times 10 to the minus 6, because we can see that over there. And so we just leave it like that. And then we can put here 1.3 times 10 to the minus 6. Okay, to get F alone, you're going to say 3 times 10 to the 8 divided by 1.3 times 10 to the minus 6. And if you work that out, you should get 2.31 times 10 to the 14. And that's always measured in hertz. Okay, now we can take that frequency that we just found and we can use it over here now. So we could say that the energy is equal to Planck's constant. Now Planck's constant is a number given to you on your formula sheet. And that Planck's constant is always going to be 6.63 times 10 to the negative 34. And then the frequency that we just found is 2.31 times 10 to the 14. Okay, so if you go ahead and then type that all in on your calculator, you should end up with a value of 6.63 times 10 to the negative 34. Okay, 1.53 times 10 to the negative 19, and that'll be measured in joules, because energy is measured in joules.